August the 9th, 2021 saw the release of a major new climate report, the AR6, or the Sixth Assessment Report by the Intergovernmental Panel on Climate Change. The report is the result of years of work by hundreds of the world's best climate scientists. It summarises our latest understanding of the physical basis of climate science, the state of the climate now, and what we might expect of the future of the climate. My name is Doug McNeall, and welcome to Mostly Climate, the climate science podcast from the Met Office. 8 years have passed since the fifth assessment report was published, and this latest version, the sixth assessment report, includes the huge amount we've learned over the last 8 years of climate science and delivers a far greater confidence and stronger language about the state of the climate and the future. So to discuss the report, what's in it and what it means for our understanding of climate change, I'm joined by my co-host, Dr. Rosie Oakes. Hi, Rosie.
Hi, Doug.
Rosie, let's have a little chat. Let's think about the scope and the scale of the report. And I think you've got some facts and figures and some of the structure available at your fingertips.
Yeah, so the release of AR6 is really exciting, especially on the run up to COP26. So I'll just talk you through what it looks like. The summary for policymakers is structured into 4 sections. So there's firstly a current state of the climate summary. And then the second section looks at possible climate futures. The third section looks at information about risk management and regional adaptation. And the fourth section is all about limiting future climate change. So it's a really practical overview from what's happening now, what could happen, and what can we do about it.
It's a really large document. I know these documents have got larger and larger. We've got on through the 6 assessment reports. So what's the process of writing and who's involved?
Lots of people are involved. Specifically, there are 234 authors from 66 countries, and there are over 500 additional contributing authors. So that is a lot of people involved. And it took almost 3 years to write this document. So it's a huge amount of work from scientists all over the world.
And I understand there's a few sort of interesting features, and that there's a summary for policymakers signed off, and there's a particular reason that it's signed off by governments across the world.
The governments from across the world get together to look at this document and sign off the different sections to make sure that they all are bought in to the science that is in the report. And that's a really important part because climate change is a global challenge, and so we need to tackle this as a global community.
That's great. So how does it read? Are we looking just for the scientific community, or is there a wider readership as well?
The scientific community are definitely interested in this report because it shows the advances that we've made over the last 8 years. But it's not just about the science, it's about actions that can be taken as well. So there's a summary for policymakers, and there are different summaries aimed at different audiences. So this should be theoretically a document for everyone, but I can understand if people see the big long document and feel a bit overwhelmed by it maybe, but hopefully our discussion today can help break that down for people.
And obviously this is a really important document for informing policy. We want to make sure that we trust the science in it. So what are some of the things that have gone on in order to make sure that the science in it represents our true state of knowledge?
Scientists are always really keen to make sure that the work they're presenting is based on the data that they have and previous studies that have happened. So in this AR6 document, there are over 14,000 new papers that have been reviewed. So that represents a huge amount of science from around the world that has gone together to be synthesized into this report.
I understand there's a huge amount of expert review as well.
Drafts of the report are shared with the scientific community and asked for comments, and nearly 80,000 expert reviewers and government reviewers commented on this. I wouldn't have liked to be the person who was inputting all of those comments and reviewing them to reshape the next draft. But I think that's really the amazing thing about this document is it does represent a big summary of the science that's happened. There are contributors from over the world and reviewers from over the world.
And maybe we'll find out actually what it feels like to be involved in such a large process, as we're really pleased today to introduce 2 guests, both at the Met Office and involved in writing and reviewing the report. So here with us today are 2 Met Office Science Fellows, Dr. Helene Hewett and Dr. Chris Jones. Hi, Chris.
Hi, Doug. Hi, Rosie.
So Helene, maybe I'll start with you. I understand were you a coordinating lead author? Could you tell me what that means?
Yeah, so as you said, I was a coordinating lead author of the chapter which was assessing ocean, cryosphere and sea level change. So as the coordinating lead author, you have a lot of responsibility. You're giving scientific leadership, you're leading the whole project for the chapter, and you're leading the people. And we had a particular focus on diversity and inclusion, so that was always in our mind as well.
So how many people, Helene, are involved in writing your chapter? How many people are you marshalling in that process, if you like?
So in our chapter, there were 3 coordinating lead authors, 15 lead authors, 5 chapter scientists, and 74 contributing authors, and 3 review editors. And of those 80,000 comments for the whole report, our chapter alone dealt with 10,000 comments.
Wow.
Oh my goodness, that's a lot of comments.
That's huge. Well, anybody who's been in a room with 3 climate scientists knows there's 4 opinions. So that must have been a massive effort. And Chris, we'll come to you. You were a lead author on Future Global Climate chapter. Can you explain how that happened?
My main roles as a lead author on chapter 4 is on global projections. It's the projections of global scale metrics into the future. There's a lot of ties between projections and carbon cycle. We're talking about carbon budgets to achieve climate targets.
How does the information in AR6 in your chapter differ from what was available in the previous report?
One thing that was really novel this time was the ability to bring in multiple lines of evidence from past climates and things we've learned over the last few years together with the climate models. So in previous reports, whenever we look to the future, we rely almost completely on the climate models to tell us what the global climate might look like under various different scenarios. But now we're able to combine that with more evidence of how the climate has changed in the past to restrict some of those projections. So some of the models, for example, if during the historical period they've warmed too quickly, we might want to reduce how much we think they warm in the future, or if they've warmed too slowly, we might want to kind of squeeze that up a little bit. So overall, we're able to use, the technical term is emulators, or simple climate models that are calibrated to represent what the more complex numerical models do, but can also bring in other lines of evidence, and that enabled us to make some tighter predictions, I think, of what might happen in the future.
So as somebody with a background in geology, this is really exciting for me. I've spent a lot of hours looking at pieces of plankton and trying to measure them to tell us about the past world. How far back in time do you use information from?
It's amazing what the paleo community can do. They can literally dig up fossils of plankton from 1 million years ago and tell you which way the sea was flowing at the time. And there's a huge wealth of information, and there's always been an IPCC chapter on paleoclimates. We've always had that knowledge of how climate has changed in the past. That's not in itself a new field, but being able to merge that seamlessly with the projections is what's new.
And what's that done to the overall projections in terms of what we're estimating for the future?
I think it's probably reduced some of the uncertainty. So we know that the climate has warmed to date. We know that it's going to continue warming, but there's always a level of uncertainty. We don't know with exact precision how much warming we're going to get. So we examine different possible future scenarios. So we look at what would happen if the world cuts greenhouse gas emissions very strongly. What happens if they carry on emitting as they are today? And under those different scenarios, we can make different projections of how much warming we'll get and when we might reach certain levels. So as you know, the Paris Agreement aims to limit warming to no more than 2 degrees above pre-industrial and to try and limit it to 1.5 degrees. So we can look at when we're likely to reach those levels under those different scenarios.
Sounds really useful in terms of planning for the future. I know that when we work with people internationally, one of the biggest problems is if there's high uncertainty, it's hard to determine exactly what they should do and where they should invest their money. So it sounds like that work will be really helpful, both from a scientific perspective and from a more applied perspective. Helene, can I ask you the same question? So in the chapter that you led, how has the science advanced since AR5?
We've seen an amazingly fast amount of progress just even in the last 3 years. So, in our chapter, we saw new observations of the ocean, the ice sheet record. We had people working on extending that right up to the present day, high resolution glacier observations. We have new models or model experiments that we've looked at. And I think we talk about narrowing the uncertainty, but I think a big thing in our chapter was that we actually know the known unknowns a little bit better, which mean that we can look at these low likelihood, high impact events. So for sea level, for example, we have a likely range, but we've created a better framework for how we explore this deep uncertainty associated with sea level and whether the ice sheets will produce a large contribution.
I'd like to dig into that, if that's possible, a little bit. So one of these climate impacts that we really are sure about, and is in some ways irreversible, is sea level rise, isn't it? Could you just outline the processes which cause sea level rise and tell us a little bit about the headline results?
There's two major contributions to sea level rise. First of all, as the climate warms, the ocean has an amazing capacity to take up heat. But as water warms, it expands, so the volume increases. So that's one way that sea level rises. The second way is when water that's stored on land as ice, either glaciers or ice sheets, melts. As that melts, it pours water into the ocean. So you're adding water to the existing ocean. So that's how it occurs. So that's why we look at all these different contributions and add them together. If we continue to warm as we've been doing, the sea level will rise by up to a metre by 2100. But it will continue to rise beyond that to 2300. And there's big uncertainty associated with that, particularly whether the Antarctic ice sheet or the Greenland ice sheet will produce a large contribution, and that increases the uncertainty. So we say in the summary for policymakers that we can't rule out sea level rise of approaching 2 metres by 2100 and much higher by 2300. I think it's really important to remember one other fact, which is that extremes that occurred once per century in the past, in the future, we can expect to see occurring every year.
What does this mean in terms of impacts for communities around the world?
Well, 1 metre of sea level rise would have a dramatic impact on coastal communities, particularly in highly populated areas, but also for small islands, this would be devastating, and lots of mitigation and adaptation will be required.
Chris, one of the headline results that I saw that you might have a view on is this idea that carbon sinks get less efficient at higher warming levels, and the science on this seems to have firmed up. So our listeners might not know about a carbon sink. Could you explain what a carbon sink is and what the latest science on this is?
Carbon sinks are the reason that climate change at the moment is only half of what it could have been. So we know that we're putting carbon dioxide into the atmosphere by burning fossil fuel. Natural ecosystems, so whether it's plants, vegetation, rainforests, or whether it's in the oceans, they absorb carbon dioxide out of the atmosphere. So the more we put into the atmosphere, the more they absorb. And over the last few decades, they've absorbed approximately half of all the emissions we've put. So the amount of CO2 in the atmosphere has only increased by half as much as it could have done. And so that natural service is slowing down climate change. But we know that that might change in the future. We know that these natural sinks, we call them, so they absorb the carbon, they're sensitive to the climate itself. So if it gets too hot or dry, for example, we know the forests might not function. So, we know that the more we put into the atmosphere, probably the less of this natural service we're going to get back. So if you like, the harder we hit nature, the less help it's going to give us in return.
So that links in with something that I think was one of the major outcomes of the report, this idea that climate change isn't a thing for the far off future. We're seeing the impacts now. Many of our listeners will have seen pictures of forest fires and really extreme weather. So you're saying that the extreme weather, sort of extreme heat and forest fires and those kind of climate impacts that we're seeing right now could have a really big impact on this natural service that these carbon sinks provide?
Yeah, I think that's absolutely what we're seeing. I mean, there's been a really big advance in our understanding of how individual events can be attributed to climate change. So there's always been a conundrum that we say you can't ever prove that a single event was caused by climate change, but we can look at the risk that has changed. We can talk about how the extremes have changed, become more likely or more intense. So we know that, as you said, there've been a lot of fires in the news in the last 12 months, a lot of flooding, and the risks of those things are higher now than they were, a few decades ago. And we know that, every increment of warming is likely to make these things increase further. So there isn't a particular threshold where it's safe up to a certain level and then it becomes dangerous. There's kind of a gradual change.
And Helene, this speaks to something that you mentioned earlier, which is these known unknowns. We've had a podcast in the past talking about some of the tipping points that we've seen in the Earth system. Can you explain how the risk of passing those tipping points in the oceans and the cryosphere might increase? And it sounds like you've adapted the language in your chapter when it comes to the projections, incorporating the sort of idea that you might cross a threshold, or the risks of crossing these thresholds in the system get higher as the warming continues.
Well, I think the way we like to talk about it, Doug, is about sea level rise, which can't be excluded. So, for example, one of the major risks for a high amount of sea level rise in the future would be if what's known as the marine ice cliff instability around Antarctica became very widespread. And this would mean a large loss of mass from Antarctica. And so we're not saying these events are going to happen, but for very risk averse users who need to know what the worst case scenario is, that information is there in the chapter, and we assign it low confidence, which means that there's limited evidence and low agreement between the various strands of evidence. But nevertheless, we just can't exclude it, and that's what's shown there.
So these are things that are sort of low probability and we're very unsure about. We just can't exclude them, and so they need to be on our kind of risk radar, if you like. And you mentioned the marine ice cliff instability. Is that right? Could you explain the process that happens there?
So basically around Antarctica, there are ice shelves. When warmer water comes under the ice shelves, it starts to melt the ice shelves back. As the ice shelves disappear, that allows the marine terminating glaciers to discharge more into the ocean. And the marine ice cliff instability means that cliffs form, and the idea is that if cliffs become over a certain height, they will collapse more readily. It's not a well observed process because we haven't seen it in the present day, but there is some evidence to suggest that it was very important in the paleo history.
So, Chris, I noticed that the language for the AR6 has changed significantly from the AR5 in the summary for policymakers. It's very much aimed at sort of non-climate experts. Can you explain how important it was? And then maybe afterwards we'll talk about, what this AR6, this big climate report, is for.
The language is very carefully stated. So I think, as we discussed at the beginning of this piece, that this report is accepted and signed off by all the world's governments. So we have to phrase it in a way that is scientifically defensible. So we always have levels of confidence. There are some things we're very confident about. There are some things we're not sure about. Helene was discussing the ice cliff instability. We know it could happen, but there's a lot of uncertainty around it. So the language now is much more confident than in previous reports. We know that the climate is changing and it's caused by human activity, and there's no real question about that anymore. We know that it's having impacts on people right now. It's not just a question for the future, but we also know much better what we can do about it. So hopefully those kind of nuggets are coming out much more clearly in that summary, so that there's no doubt left in terms of the policy negotiations of what we need to do next.
So that gets to the root, really, of what this is for. So we're informing global policy on what to do about climate. Can you explain very broadly how that happens, and also, I guess, what comes next?
Yeah, I mean, so this is where I'm glad I'm a climate scientist and not a policy negotiator, because the science is kind of the easy bit. We know that if we want to stop the world warming, we have to stop emitting greenhouse gases, and that's pretty simple. So we know we've got a finite amount of CO2 we can put in the atmosphere to stay within certain warming levels. But how we allocate that between countries, how do different countries reduce their emissions? How do you fairly share out that remaining budget between developed countries, developing countries, high population, low population, places in warm climates and cold climates have different energy requirements? That's a really, really difficult subjective discussion.
Now, Helene, this was a massive report. This is a massive effort. It's a huge amount of science. I hope you got a holiday afterwards. But I'm interested, I guess, in what comes next. What is the interesting science that's coming out? What should we look forward to in terms of the new climate science?
Well, I think, the IPCC report, it's not policy prescriptive and it's not prescriptive on future research. So that's really important. But I have some, particular things that it's highlighted for me. While the limiting emissions is really important for warming now, there's a long-term picture for sea level, because sea level has a slow response time scale because of the ocean warming and the ice sheets. And there's big uncertainties around ice sheets, as I've talked about. And so for me, that's the next really big, exciting thing that I hope we can make progress on in the next 5 years. Better understanding of ice sheet processes, better understanding of how the oceans and the atmosphere control the ice sheets.
From all the work in your chapter, Helene, all those authors, all those review comments, if a policymaker could just take one thing away, what do you hope they take away from your chapter?
I hope they take away the message that it's only by limiting warming that we can reduce sea level rise, the rates of sea level rise into the future.
And Chris, same question to you.
Basically, do something now. There's a wide range of possible futures. We can still control which path we follow, but the actions that determine that need to be taken now. So we need, the urgency is there.
Well, my thanks to co-host Dr. Rosie Oakes and our guests today, Dr. Chris Jones and Dr. Helene Hewett. I'm Doug McNeall. Our producers are Clare, Nasir and Grahame, Madge, and the editor is Adrian, Holloway.
Mostly Climate is a podcast by the UK Met Office.